before I start on this, there were a couple of points from the exam. The very first problem, a number of people use Z instead of T. If you look back at the problem, it specifically said, I've given you the sample standard deviation as opposed to population standard deviation. That's the key that tells me which one of those tables I should use. And since I had 10 samples and a sample standard deviation, that was a T, not a Z. I saw this in a couple of places. A number of you had the formula you needed on your formula sheet for things like, what's the population I need, and then copied it over. If you didn't have the formula you should have used, go find it, add it to your formula sheets. You get to use them again on the final, and you'll see this stuff there again. Meanwhile, if you have questions about your grade for the exam or in general, come talk to me. I'll be glad to do this. I believe on Canvas at this point, you can start playing with what do I need on the final to get by looking at the grade book on Canvas. Okay. Analysis of variation. I want to do another two-factor problem without replication. So here, problem number 23 on page 433. Driving times, minutes, from the airport to each of 4 downtown hotels is recorded live for 5 Uber drivers. Does the sample provide sufficient evidence to conclude there is a significant difference in treatment means? Okay, wait a minute. We talked about a treatment mean versus a block when we talked about a randomized model. Remember, I was talking about the soil conditions on Monday, and I said, well, we could be looking at only wondering about the effects of the fertilizers and not really. So we'll assign people randomly. With this layout, there's a convention. One of the factors is the treatment, one of the factors is the block. Find me which is which, based on our information from Monday or from the textbook. Which is the treatment? I'm going to fill in one of those 2 blanks with the word column. I'm going to fill in one of those 2 blanks with the word row. Are the rows the blocks or the treatments? Are the columns the blocks or the treatments? There's a default when we do a 2-factor ANOVA. Max? Right. So back on page 429, it says when we are doing a randomized block model, then the default is that we call the row effects blocks and the column effects treatments. So treatments are the columns. The blocks are the rows. Okay, wait a minute. So I'm trying to tell if there's a difference based on which driver I have, not which hotel they're going to. Because if I go back and I look at my data, the treatments are the drivers. So I want to know, if you're coming from the airport, is there one driver that's particularly faster or slower than others, or are they all just different on average, regardless of which hotel you're going to? So I don't care about the hotel, I care about the drivers. Let's jump to Excel and do the ANOVA. This is question number 23 here. Share. Bing. Okay, so there's my data set up exactly the same way as the table I was just looking at in its randomized block format here. So with that data, I'm going to run my ANOVA. I go to the data tab, data analysis, and I pull up two-factor without replication, because there's only one data for each combination of row and column. Input range, where is my data? Right, my data is here. I didn't put labels on it. Well, yes, I did. The top and the hotels are highlighted, so I'm going to use that. There are labels, 5% significance, so I'll do a 0.95, put it all in a new worksheet. Okay, here's the results. Up here, I have the summary data at the top for whether or not the row effects and the column effects are listed. You'll notice I get the averages for each one, I get the variances for each one. But what I'm really concerned with is the ANOVA itself down here. Sources of variations. Which p-value am I looking for? One's going to answer the question for me, Mike. Right. We said the treatments were the columns. So I want the columns data here. So we have a problem. What am I supposed to do with my null hypothesis based on that number? I reject when my p-value is smaller than 0.05, because that was the alpha we chose. Or I would reject if the calculated F value is smaller than the critical F value. That is the most borderline possible case I could possibly have, isn't it? The p-value is just a little bit big, 0.50006, but 3.25902 versus 3.25917. The calculated value is smaller than the critical value. I'm supposed to reject when I'm further out. That says don't reject. But by the skin of its bloody teeth, there's a borderline effect here. Which driver I get is not statistically significant. On the other hand, if I'd chosen a different alpha, if I'd chosen alpha equals 0.025, then it would be a clear-cut case. If I'd chosen alpha equals 0.1, it would be a clearer case based on that p-value. If I chose a 0.025, I would not reject. That number is bigger. If I chose the 0.1, I would reject it because that number is small. The fact that I chose 0.05 and this data is right on the frickin' edge is showing me the limitations of this information. This is where statistics is a little bit more of a loose behavior than I would like it to be. I'd like to have clear-cut decisions. The data is inconclusive for me. According to this, there's almost a reason to say, yes, your driver makes a difference. But it's right on the borderline. Can you say for certain the driver makes a difference? No. Not 95%. or 5% sensitivity. What about hotel? Does it matter which hotel I go to? We said that that was one we really weren't looking for because we were only concerned in the question about the treatments, but let's look at the blocks as well. What does the row effect tell me? It simply doesn't have a statistically significant effect. It may actually have an effect, but it's not enough of one that the variation in drive time is caused by picking a particular hotel. If we go back and look up here, the averages aren't all that far apart. The variances are pretty large, but the means aren't all that different. So I can't say that, oh, if you pick hotel 2 over hotel 3, you're going to get there a lot faster because the variance in hotel 2 is larger. The variance in hotel 3, even though the average in hotel 2 is smaller than the average in hotel 3. So it might still take you longer to get to hotel 2 than it did to hotel 3. Driver, that might make much more of a difference. Problem is here that it isn't a clear-cut decision. I will say that driver has more of an effect than hotel does because the p-value for driver is substantially larger. Sorry, for driver is substantially smaller than the p-value for hotel. And the closer it is to 0.05, the more of an effect it has. How can I come up with a better answer? What can I do to improve my knowledge about what's going on in this situation? The answer actually isn't here. Answer instead is here in the data itself. This is my problem. I only imported one trip from the airport to a given hotel for a given driver. I could say to these Uber drivers, I need more trips for me to tell whether or not you matter or the hotel choice matters. I could change the model by looking at replication. If I can gather additional data, I might be able to get more information. But as I gather more data, I introduce another source of variation. So if I switch to a model with replication, then I've added a new effect. Now, it depends on the way I gather the data. Let's say I go to these Uber drivers and I need to tell me 2 trips each. So instead of just having one number in each of those boxes, I want 2 numbers in each of those boxes. Then I have what's called balanced data.
You don't always have balanced data, but our process will work regardless of whether we have balanced data or not. I just think balanced data is more useful. And when we have balanced data, then I get both the main effect of each factor, but I also get an in factor, an interaction effect as well. Since this is analysis of variation, I'm looking at where my variation comes from. And now this new source of variation, the interaction effect, so maybe one driver and hotel combination, when this driver goes to this hotel, they know a shortcut. They're going to have a particular effect. Wait a minute, I wasn't using I was using J and K. A, J, B, K. So really this changes my model a bit. I now have this new possible variation involved. We're going to call this a full factorial model. Factorial here does not mean the exclamation point that we used it to mean in probability. It means combinations of factors. So we're using the word factorial a little differently. So my data setup is going to change, and my data setup is going to look differently. Close this one. 25. Something like this. Notice that in each block, this is problem 27, I have multiple pieces of data within each block. So let's see, what is this problem all about? This problem is about a market research firm is testing reactions to new shampoo. 4 regions. So where we are, Northeast, Southeast, Midwest, West, and 4 age groups, youth, college, adult, senior. And I want to know, on a 5-point scale, what do people think of my new shampoo? We'll come back to that. Now, I have a question for you. I have 3 possible variation sources. I have sources from the factors in the rows, sources from the factors in the columns, and I have the interaction effect. What's my null hypothesis? I'm going to test something. I need to know what I'm going to test. I think it will help if I write down the model I'm thinking about. So remember, we thought of this as like a line, and we said, oh, it's possible that my data, my response variable, will have some big overall average. And then there will be some effect from the row and then some effect from the column, and then we're adding this interaction effect. Oh, and then there's some possible random error, which doesn't matter about J and K at all. So this is the new piece when we do replication. That's the piece that wasn't there in the other model. It was just AJ and BK. Now we're adding this. So what hypotheses am I going to test here? What was I testing with the last one? About the AJ and the BK.
It would be just no variation in rows and no variation in columns.
Right, so now I'm going to add. Exactly. So my null hypothesis, I have 3 null hypotheses. The A effects, the effects caused by the rows, are nothing, which, based on our last one, would be the drivers. Sorry, yes, the hotels. Hotels were the rows. So which hotel I'm going to doesn't matter. The B's, which driver I'm using, doesn't matter. And the interaction effect, no particular driver and hotel combination is particularly efficacious. Make sense? I've added this new idea of the interactions. What are my alternate hypotheses? In all 3 cases,
Like one of them.
at least one is different. Okay. Again, I don't plan on doing these calculations by hand, but I want to look at the setup. So let's go back to that shampoo problem. Question 27 is the shampoo problem. And let's take a closer look at what's going on here. Here's my data by region, by age group. Notice in each group, I've got 5 surveys. I've reported the average from 5 surveys for every group, for every age range, for every data location. I don't know squat about marketing shampoo. But this market research firm has done these surveys and recorded me this information. Tell me why you think either of these factors might be important. Why would age matter? That's what our row effect is. Age group. Come on, y'all are in this. Why would your age change your opinion of a shampoo? Nice. Sure, marketing effect might make a difference, but I want you to use this product for a week and then come tell me what you think. Here are your flowery cute scents. Here's a bubblegum scent. It makes a big difference, right? This thing smells like a tar pit. I don't want to use this on my hair. I make a hell of a difference. Body chemistry. My body chemistry changed dramatically between the time I was 18 and today. So what age group I'm in is going to make changes to the way my hair grows. Hairstyles change. When I was 18, my hair came down to the middle of my back. By the way, it also came down to my forehead. So it's been a long time since I've had hair. But I had a lot more hair. I took very different care of it. Makes a difference. So where you are, what hairstyle you're wearing now, location. Why would region of the country matter?
Levels of humidity.
Humidity, weather conditions. If you live in Nevada, I'm pretty sure your hairstyle is going to be different than if you live in Minnesota, right? I got really upset with having one at one point in college because I went to the University of Florida. And I just said, no, I'm sweating to death, cut all this crap. That made a difference. So, interaction effect. What does interaction effect mean here? Maybe one group in one region has a particular reaction, positively or negatively, to this particular product. Maybe the combination of being a college student in the Northeast makes a difference as opposed to being a college student somewhere else, as opposed to being in the Northeast somewhere else. Maybe there's variation just within that. For example, if I look at this one block, those numbers are all pretty close together. But if I look at a block over here, those numbers are even closer together. Well, except for that last one, right? These numbers are all really close together. So maybe one block has less or more variation than another. Let's run an ANOVA. Let's see if any of this is actually making a difference. I'm doing an ANOVA, 2 factors with replication. Data, analysis, with replication. So I say, okay, and it says, where's your input? My input is here. How many rows per sample? I need to count in the box. Now, in this case, we have balanced data. So I can say it's the same, it's 5 rows per block. Even if we have unbalanced data, I'm going to take the largest block size. Again, I'll do 5% for now. We can change that and adjust as we see fit based on the needs of the market survey. But that alpha being 0.05 is almost always standard. Go. Okay. I got a lot of information here. Maybe I need to shrink this so we can see more of it at once. All right. That's all the summary information. I've shrunk it down so I can see it better. I put this on the examples for in class. If you want to pull it down and look at it on your Excel page right in front of you. But let me see what this data is broken up into so I can try and figure it out. What I've got here is a mean and a variance for each block. So in the upper left corner here is the Northeast youth block. 5 with a total of 20, an average of 4, and a variance of 0.05. And if I go across that first row, that's all the youth section. So all the way over on the right, that 5th column there, that's going to give me row summaries. Way down here at the bottom, I've got 4 column summaries. So I can look at the column summaries, the row summaries, and the individual block summaries. When we did it without replication, I only had 1 data value in each block. So I didn't have a sum, an average, and a variance within the blocks, I only had a number. That's why I only got row summary and column summary for the non-replication one. Here, I get more. Let's look at the actual ANOVA results themselves. All right, wait a minute. Have now another listed p-value. The p-value I have now includes an interaction effect. So, first question. Rows, columns, interactions. It says sample. I'll live with that because I didn't label the rows or the columns. So the rows have an effect. Really, really, really small. 5 times 10 to the negative 14. That's 13 zeros in front of that 5. I can also look at the F value. The calculated F value is 37, and the critical one is 2.7. That's a huge, we're way out in the tail. That is definitely in the reject region. What does that mean? Rows were which part of the data? So if I go back and I look, rows are age. Age group matters or not? I rejected the null hypothesis. What was the null hypothesis for the rows? We wrote it down. What was the null hypothesis for the rows, for our A's? So the rows had no effect. You told me to reject that. If I reject that, it means the rows do matter. And that means that the age of people matters as to how satisfied they are with our shampoo. It's not just that I rejected the null hypothesis. I need to now turn that back into something I can go back to my boss and say, yeah, age matters. We're marketing to the wrong group. The cartoons need to come off or whatever. Now I can go back to the row effects and I can say, oh, I am now sure that the rows matter. Let's look at the row effects. Here, the average is 3.9. The average is 3.8. The average is 3.5, 3.3. Our older people, adults and seniors, don't like this product as much as youth and college students do. If we want to market this more appropriately, we should aim at that young demographic. Under 25s are going to get us more sales than over 25s. Maybe I should put the cartoons back on the cover or whatever it is. I'm marketing more satisfaction. I'm seeing more satisfaction in younger clients. Column effect. Does the column matter? P-value is bigger than 0.05, like 0.65. I can also look at the F value. The calculated F value is 0.55. The critical one is 0.27. Sorry, 2.7. So with the F being too small, I'm in the white region of the graph. I don't reject. My P-value is too big. I'm not out in the tail. And that means what? The location is not important. Satisfaction does not depend on where my people are located. They're just as satisfied in the Northeast as they are in the West, as they are in whatever my 4 categories were. Interaction. Is there an interaction effect? And notice now that my F critical change. Why did my F critical change? F critical change because the number of options changed. I had 4 rows, 4 columns. That's why the degrees of freedom is 3 in each of those. Degrees of freedom for interaction is 9. My degrees of freedom are counted differently here. And so my critical value changes. But as long as the p-value is smaller than 0.05, yes, there's an interaction effect. Questions? By the way, that last row within, that's variance between each of the individual data pieces as if they were considered one giant pool and not segregated. That's our epsilon at the end of our bit, is our variation there important. I know there's an interaction effect. I don't know what it is. What questions do you have at this point? How can I figure out what the interaction is? I'm going to go back to the textbook for a moment, and I'm going to actually make a plot. I'm just going to make a line graph. I'm going to graph the interactions. How? By graphing the actual averages by row and by column. When I have lines that don't cross, notice that there are substantial differences as A changes. There are substantial differences as B changes. But because these lines don't cross, there's no interaction between those effects. Here, both factors are significant because those lines are far apart. Clearly, B1 versus B2, as well as A1 versus A2 versus A3, both matter. But here, when I see lines crossing like this, then there's something special about A2 and B1 that makes it lower, and A2 and B2 that makes it higher. There's some crossover between the A's and B's. So I'm going to look for crossing versus not crossing. And that will help me understand where I see interaction effects. I might not be able to nail down exactly what the interaction effect is, but I can tell you where I see it. Let's go back to problem 27 and take a look. If I graph by age. So notice this first set of 4 data points, that's the Northeast. The second set of data points is the Southeast. The third is the Midwest, and the fourth is the West. I got lines crossing all over the place, huh? There's an interaction here. So region, interaction. We said age group mattered more than region, right? Take a look at the blue line versus the purple one. Youth versus senior. Let me zoom in a bit. This is the youth data. This is the senior data. Those lines are almost parallel, aren't they? But they're clearly separated. That bright blue line is always above that purple line. There's no interaction between them. The senior opinion of this shampoo is always lower than the youth. Age has a clear effect. There's an interaction for these other 2 groups, especially in this third group, the Midwest. So there's some interaction. People in the Midwest, the young people are less fond in the Midwest than they were in the red and green regions, which are college and adults. So the youth in the Midwest had a particularly different opinion. Let's switch rows and columns. Again, now I've got each of these colors representing a single region. Midwest is the green region. And we go youth, college, adult, senior from left to right. Oh, that green line crosses all three of the others repeatedly. The Midwest is a different type of marketing region for us. For this product, for some reason, the Midwest region has a different opinion of this than the other regions. I don't have specific rationales, but I do have the ability to say, oh, that's how I can tell that there's an interaction. It's the Midwest as opposed to the other regions that are pulling our data values. It's youth and senior are almost in lockstep, regardless of region, but there's a little bit of crossover here. And I see that crossover better when I look by region than the other way. Questions? I could now have a closer idea of doing a particular t-test or particular paired test. Let's compare just the Midwest region with the East or the Midwest region with the West. Let's do a much more localized t-test. And then I can see how substantially different they are. Maybe I can start ascribing some cause to that rather than just correlative effects. Questions? This is the same information. I just stripped it out and moved it up so I could see it better. Here, I just stripped out the means so that we could see those, right? This is what I made the plots from. I took the means from our summary here, because I've got average for each row and each column. So I can just strip that data out to create our overarching plots. Questions? This idea right here, this idea treats my factors like this is the model of a straight line. I have a number plus some effect based on the row, the column, and the interaction. I would like to examine this idea more closely. I would like to know if it is possible to quantify how much a change in region changes people's opinion of the shampoo. That's a little harder with categorical data like we do in ANOVA. So I'm going to switch back to doing numerical data. So I've got a question. Does the circumference of your head relate to your height? I don't know. But if I go out and I start measuring people's heads, and I measure their height, or I just ask them, how tall are you? Measure your head. How tall are you? Can I see if there's a relationship? wait a minute, I've done this already. Back in chapter 4, I built scatter plots. I'm gonna take this idea of a straight line and figure out how those trend lines on the scatter plots work. That is our stuff for next week. So that finishes chapter 11 on ANOVA. Your homework for that section will be due on Wednesday. And we will start talking about linear effects on Monday. I will see you all then. Have a wonderful rest of your day.